All right, in this section, we're going to talk about inference. So to this point, we've done the scatter plot. So we looked at the scatter plot and we used our opinion to figure out whether it's a positive linear or non-linear relationship. Then we calculated the correlation coefficient, the R, right? And that just told us how good or bad it was. But we weren't sure what the break point is between good and bad. We made a guess as to what we thought it would be, but we didn't actually prove it. And we calculated r squared, and we talked about how x and y, as far as variance, interrelate, basically. So the last is to do correlation. So basically, the important things for linear correlation is, one, the data has to be random. So at one point, each point is selected randomly, or each coordinate, right? They're independent, obviously. They generally shows a linear pattern when you do the graphing. The outliers have been taken out. Normal equal variance. The population of x at each value of y at each value of x follow a normal distribution, and with the same standard deviation population of y for each value of x, basically. Okay, so as a global model or a population model, they tend to use so obviously we do y hat equals a plus bx for the sample model, right? And we make predictions with this, but this is the population one. Notice they're using alpha and beta instead, which is the Greek letters, right? So when it's a population, it's beta for the slope, whereas the sample is the lowercase b. So obviously in statistics, we have always been doing English letters as sample, and then population is the Greek letters. And I've attached two different things here, a text and a step-by-step video on how to do this stuff if you want to look at that later. Okay, so as far as the hypothesis test goes, we're going to do, you use rho, which is the population correlation coefficient, and you assume it's 0, which means there's no relationship whatsoever, or no linear relationship. Because basically the way it works in stats is you assume there isn't something, and you have to find enough evidence to have something, basically. So we find enough evidence to say that it is the alternative hypothesis, which means we reject the null. So not equals means we found enough evidence, right? Which means it's significant to what we found, and it is a linear relationship, basically. We're not going to bother doing the one-tail ones. We could do those, but that just shows us specifically left or right tail. We don't need to do those. That's just an additional step. Just saying as linear is good enough for now. The t-statistic or t-stat is calculated with the r and the number of values. Okay. The degrees of freedom here is n minus 2. And you might say to yourself, well, we did degrees of freedom before for t, and it was minus 1. Yes, that's true, but that was in a different chapter for a different topic. And that was a one variable topic. This is a two variable topic. So the degrees of freedom actually changes based on the topic that you're doing. And there's other things besides the use degrees of freedom, but specifically we use minus 2 here. So the confidence interval for the true slope, you use the sample B, you use the t alpha divided by 2, which we've done in the past, the same thing, and then the standard error of the b. So there's a b there. It's the standard error of b, and this is the formula here. And we're not going to do that in this section. We're just going to do the hypothesis test. The confidence interval comes later. Okay. So we're going to do the car problem, the absence problem, and the pupil problem hypothesis test, essentially. So I made another tab in my spreadsheet, and I copied over the data here. So n here is, how many do I got here? 6, right? The n here, actually I don't even need to do this. What I'm going to do is I'm going to click equals, go back to here, and click on this, and hit enter, and drag it down so I can save time. So I have to do this over again. I'm going to go down to here, click equals, go back to 12.3, click that, hit enter, and then drag it down. That just saved me some time of redoing it all. And then lastly, equals, go to 12.3, click it. Oh, sorry, that's the one there. Hit enter, drag it down. Okay, so we want to calculate t-stat and t-crit. Okay, so if we go back to our notes here real quick and copy the formula for the t-stat. Right, that's the formula we get there, right? I can shrink that down a little bit. Okay, so we'll get it out of the way for now. All right, so it's the r value times the square root of parentheses n minus 2, close paren, divided by parentheses 1 minus r to the second power. The mistake that I often see is people not putting these sets of parentheses, right? If you don't do that, it's not going to follow the order of operation, or only do 2 divided by 1 and not the rest of it, right? So make sure you do that. Okay, so there is our t-stat value, basically. So it's just using these ones, right? So I think all I have to do is copy paste, to be honest with you. So I can copy and paste. Yep, just using those, and then copy and paste. Oh, I didn't do that right. Copy and paste, and there is our t-stat value there. Okay. All right, so now we got to get our t-critical value. So you have to think about the values that we actually have here. So this first one, right? Alpha is 0.05. That's what it said, right? 0.05. Okay, which means this is 0.025, and this is 0.025. So we want this t star value right here, correct? Which means we need to get from here to here, which is the 95 plus 2.5, so that's 97.5, right? Oops. So t dot inverse 0.975, comma, notice it says degrees of freedom, so that's 6 minus 2, close paren, and that does it for us. Perfect. Okay, so the next one, what is our t value? Well, what is our alpha? I forget here. Our alpha for this one is 1%. Okay. So if we think about this one, come on, right, so we have 0.99. So this is half a percent there. And this is 0.005 there, right? So go from here to here is 99.5. So I think I can just copy this, to be honest, to there and do 99.5. Right, so it's still degrees of freedom minus 2. So I get 4.03. Ah, that's not what we want, though, because that's a negative one there, right? This is positive, positive, negative, negative. That's not the case. All right, so this is not what we want. So we're going to do this again. All right, so we got 0.99. So we want this t value here, right? So this right here is 0.05 to get there. Right, to get there, right? So we want to put 0.05 to get there. I get the same value but negative, right? Because if I did the same thing here, right, if I did 2.5, it'd be the negative value, wouldn't it? Okay. All right, lastly, what is this one here? So if I do this one is 10% alpha for the pupil problem. Okay. So if I do the pupil problem, boom, boom, 0.90. Alpha is 10, right? 10% is alpha. So that means this is 0.05. This is 0.05, right? You know, this is a positive t, so I want to get to here for t star, right? So from here to here is 95, correct? So I want t dot inverse 0.95, comma, degrees of freedom is minus 2, and there's our t value there. Okay, so we want the area and the p value. And you're like, why is it two different ones here? Well, you're going to see. So you're going to copy, paste, and paste. Okay, so if I do the area here, I want to do 1 minus t dot distribution. Click on the t-stat, comma, degrees of freedom minus 2 comma true. Well, why is it 1 minus? Because I'm trying to get to this t-value, which is 10.39, correct? And I want this shaded area here. So it's going to be this way. So I need the 1 minus to flip it from there to there. Because if I don't do the 1 minus, it's going to give me this area, correct? Okay. So that is the area there, right? So if I do this one, it's t dot distribution. Click on this, comma, degrees of freedom minus 2, comma, true. And I get this one. Notice I didn't do 1 minus because this is a negative 1, right? And then if I do the last one, it's a positive 1, so I'm going to do 1 minus t dot distribution. Click on that value, comma, degrees of freedom minus 2, comma, true. And I get that area there. Okay, so let's look at our picture now. Let's see if I can get my 3 pictures drawn here. Okay, so the first picture. Okay. My t is 2.76, right? Or negative 2.76, but I only care about the positive one in this case. And my t-stat was 10.39, which means it's in the shaded region, which means I should be rejecting the null hypothesis, which means my p-value should be less than my alpha. Well, this is half of the alpha, and this is half of the p-value, essentially, right? So I need to actually double it because it's two-tailed. Because again, we're doing a two-tailed test. So what I need to do is equals 2 times this to get the actual area. Okay, so what it works out to be in the end is this. It's a two-tailed test because we're not going to bother left and right. I calculate t-stat, I calculate t-crit, I put them on my picture. I have to double it to get the actual p-value because this is only half because it's always two-tailed for the ones we're going to do. So therefore this p-value of 0.00048 is less than alpha, right? So what does that actually mean? We should reject the null hypothesis. If we're rejecting the null hypothesis, that means we're saying that the row is not 0, that the row is not equal to 0, which means there is a relationship. Thus, there is enough evidence to suggest there's a significant linear relationship, correlation between the number of cars sold and the revenue. Okay? All right, let's try this again with the absence problem. Okay, so go to the absence problem. Okay, and I have to do the same thing. I have to do equals 2 times this for get the actual p-value, right? So if I do the picture for the absence problem, let's go down here, and I'll get the absence picture. Copy, paste. There we go. So in this case, since it was a negative t, we only care about the negative t stat. So t crit versus t stat, right? And obviously this is less than this. This is in the shaded region, which means we found enough evidence. So half of our p-value is less than half of our alpha, right? Which means we should be rejecting the null hypothesis, essentially, correct? Okay, and again, it's two-tailed, so I have to multiply by 2. So what that means is, oops, let me fix that. Okay. We assume there's no relationship, but we proved otherwise because we calculated t-stat and t-crit, and obviously t-stat is in that region, right, the shaded region, and then the p-value is less than the alpha. Therefore, we reject the hypothesis, the null hypothesis, correct? And if you reject the null hypothesis, which is that there is no relationship, that means we found evidence to say there is a relationship. So basically between absences and final grade, there's a significant linear relationship. Okay, and again, we're not doing anything as not linear. We're just focusing on linear ones. There are relationships besides linear, but we're only doing the linear ones essentially. Okay. All right, so the last one, when we did the graphing, we didn't think there was one, correct? For the teacher-pupil problem? Okay, so the teacher-pupil problem, right? We got this t-stat and this t-crit, so this doesn't quite make it to this value over there, correct? So let's do a little picture here. So if I do the picture for this one, all right, as I hand drew these earlier, okay, what you notice is the t-stat doesn't make it into the t-critical region, right? Doesn't make it. So therefore the p-value, half the p-value is more than half the alpha values. You double it, it will be the same thing scaling wise, correct? So we did not find enough evidence because in here is all the common samples, which means mine's a common sample. If it's an uncommon sample, then it's in here, right? Which means we found enough evidence to say otherwise. Because the default is you have to believe there's no relationship. And what we're doing is we're proving there is a relationship, which we did not do in this case, because clearly 0.20 is greater than 0.10. So therefore we should not reject the null hypothesis in this case. So essentially this means that we don't have enough evidence to conclude there's a linear relationship between teachers and student-teacher ratio, essentially. It doesn't mean there's not a relationship, we just didn't prove there was a linear one, okay? And we didn't do any confidence intervals also, but if we did the confidence interval, which we go back, right? This is the confidence interval formula here, which is using the lowercase b we calculated. You use the t alpha 2, right, which we calculated, and then the standard error, right, which we did not calculate. So if you calculated this and you got the confidence interval, what would happen is, in this case, right, 0 would not be in the confidence interval. In the second case, 0 would not be in the confidence interval, right, which means there's no relationship. In this case, 0 would be in the confidence interval if we took the time to calculate it, essentially.